Hey, this is Alex. Welcome back to the project. Last time we took a 30,000 foot view of the project and broke the objective down into generating and reading signals. Today we're going to zoom in and hash out the details, which will rely heavily on the use of the microcontroller's peripherals. Now, if you don't know what a peripheral is, don't panic. We'll start with an overview of peripherals, and then we'll explore the four main peripherals we'll be using in more detail. Let's get into it. You can think of a microcontroller as a small computer. Your computer has a central processing unit, or CPU, that processes instructions, performs calculations, and moves data between different memory locations. Your computer also has peripherals attached to it to interact with the user, such as a keyboard and mouse for getting the user's inputs, a monitor for displaying what the computer is doing, USB memory sticks, CD drives, and so on and so forth. Just like our computer, microcontrollers have a processor and peripherals. However, the peripherals are a little bit different. Instead of a mouse, keyboard, and monitors that you can plug in, microcontrollers have peripherals like analog to digital converters, timers, comparators, serial peripheral interfaces, etc. These allow the microcontroller to get information from the real world for processing, and also allows the microcontroller to control things through turning switches on and off, sending data out to other digital devices, and so on. Let's meet the peripherals we'll be using for this project. Number 1, PWM. PWM stands for Pulse Width Modulation. The idea here is that you turn a signal on for a certain amount of time and off for a certain amount of time. This pattern usually repeats, and so you can think of it as a series of continuous pulses, where the amount of time between the start of one pulse and the start of the next pulse is called the period, as in the time period, and the amount of time the pulse is on for is called the duty cycle. Just as a side note, period is the inverse of frequency, and you may hear me use that term as well. A higher frequency equates to a shorter time period, and a lower frequency equates to a longer time period. Here's a small example to demonstrate PWM with one of its most common applications, controlling an LED. In this case, we are controlling LED 1, and you can see it blinking. The trace signal here has a duty cycle of 50%, which means it's on for half the time and off for half the time. In this case, our overall period is 83.1 milliseconds, and that is the time between the rising edge, when it goes from off to on, to the next rising edge, off to on. And here our duty cycle, 50%, corresponds to the signal being on for 41.5 milliseconds and off for 41.5 milliseconds. So at longer periods, in this case 83 milliseconds, or lower frequencies, the switching is visible, as we can see. We're going to first lower the duty cycle, and you can see that at its lowest, you can just barely perceive the LED flickering on. And notice how in the signal trace, the signal has shrunk how long it's on for. So it's only on for 4 milliseconds, but notice that the period is the same, 83 milliseconds. And now at the highest duty cycle, notice that the light, you can just barely perceive it flickering off. It's mostly on. And again, it's on for 79 milliseconds, but the period has stayed the same, 83 milliseconds. Okay, let's return it to our approximate 50% point. And now we're going to change the frequency. As we decrease the period, or increase the frequency, notice that beyond a certain point, you can't really perceive the signal flickering. So maybe about there. So our LED appears just to be continuously on. And now as we change Let me zoom in on the signal. You can see that we're still at a 50% duty cycle, but now the amount of time has changed. So now our period is 1.4 milliseconds, and our signal is on for 730 microseconds and off for 738 microseconds. So now as we change the duty cycle, now take a look at the LED. So it appears more like it is dimming and brightening with the duty cycle changes. Now, if you recall back to the second episode to the N64 controller signal, we observed that the pulses were 4 microseconds long and were either low for 1 microsecond and high for 3, or low for 3 microseconds and high for 1. Essentially, this is an inverted PWM signal with either a 25% or a 75% duty cycle. Our microcontroller has a PWM peripheral that can generate a set of PWM pulses, and all we have to do is set the period, tell it how many pulses we want to generate, and what the duty cycle will be for each pulse. And so the PWM peripheral is going to be our main workhorse for generating the N64 controller command and control responses, respectively. Number 2, GPIOTE. Our next peripheral is GPIOTE, where GPIO stands for General Purpose Input and Output, and the TE stands for Task and Event. As the name suggests, GPIO is used for the general purpose of controlling an output, turning a pin on or off, or for reading an input, determining whether an input signal is on or off, high or low. As for the task and event, this is where the GPIO-TE really shines. The NRF54 employs a task and event structure in the peripherals. A task is an action that a peripheral performs. For example, toggle pin, or start PWM, or stop timer, and so on. An event is the result of an action or condition within a peripheral. For example, pin on to off transition detected, or timer hit a certain value, or PWM reached the end of the period. GPIO-TE can be configured for task or event mode. In the task mode, some event in another peripheral can trigger the GPIO-TE to turn on or off its pin. In event mode, a certain input condition can be detected, such as when the pin goes from off to on or vice versa, which generates an event for a different peripheral to use. We will be using the GPIO-TE to detect pin changing conditions, specifically where the pin goes from on to off, which indicates the start of our bits for the N64 protocol. And that way we can sample the controller's response at a certain time after the start of the bit to determine if the controller is sending a 1 or a 0. Number 3, timer. A timer is a counter that increments by 1 at a given rate. This means that if we know the rate that the timer is counting up, we know how much time it takes to reach a certain count value. Let's just take some examples. If my timer is counting up by 1 every half a microsecond, I know that it will take 8 counts to reach 4 microseconds. Timers have another key feature, a compare match. The compare value corresponds to some amount of time, and the timer peripheral will generate an event flag to indicate that that time was reached. So say you want to check a pin's value every 2 microseconds. You can set the compare register to the timer count that corresponds to 2 microseconds, and when the timer count reaches 2 microseconds, we can sample the N64 pin's value at that time to determine if it's high or low. Number 4, DPPI. Last up, the DPPI, or Distributed Programmable Peripheral Interconnect. It's a bit of a mouthful, but here's what it does. Remember earlier when I mentioned the task and event system for the GPIO-TE? The DPPI lets us connect tasks and events together between the different peripherals without any CPU processing. So this is really the glue that will bind all these different peripherals together and make it possible to control this tight timing of generating and sampling bits in this N64 protocol without having to trigger a bunch of different things in interrupt routines and then just hope that it all works out. Now that we're acquainted with our peripherals, let's see how they all fit together. So we're going to start with the controller side. This is we'll call it the controller connected module. When we're ready to get the button states, the controller connected module will load a command into the PWM peripheral and start the PWM generation. And at the end of the signal, on the last bit, the stop bit, we will enable the GPIOTE to begin detecting falling edge conditions, and this will be the first controller response bit. This falling edge event starts the timer, and we will have connected this event and task together through the DPPI prior to this. When the timer reaches 2 microseconds, it will hit a compare match event, and it will jump to our compare match interrupt, where we will sample the pin and save the value. We will also stop and clear the timer, and then wait for the next falling edge to start our timer again. And we will keep track of the number of bits we receive until we reach the end of our controller response. At that point, we will turn off the GPIOTE so that when we do our PWM generation, it doesn't accidentally fire. And then we will wait for the next opportunity to sample the controller. On the console side, it will be similar, except instead of generating the command and reading the controller's response, we will be reading the console's command and generating the appropriate controller response. The GPIOTE will wait for a high to low transition and start the timer when the transition occurs. And then at 2 microseconds, just like how we sampled the controller's response, we will sample the command. And then at the end of the expected command, we will determine what the command is. And based on if the command was a controller info or a controller status or accessory read or write, then we will load the proper data into the PWM. We will also make sure to turn off the GPIOTE so we don't accidentally trigger the timer starting. And then we will start the PWM to generate the response. At the end of the response, we will turn the GPIOTE back on for high to low sensing so that we can capture the start of the next command from the console. Okay, that's all for now. Thanks for watching. If you like this video, give it a like. If you want to keep up with what I'm doing here, go ahead and subscribe. Also, if there's content that you see that I'm not covering here, go ahead and leave a comment down below. For example, I'm kind of on the fence about making a video about the actual code that I'm writing to make what we just looked at happen on the microcontroller, because I just don't know who's interested in it. So if that's you and you want to see lines of code, put that down in the comments below. Thanks again for watching. See you in the next one. Bye.